Okay, so let's talk now, building off of the example we saw with the conditional distributions of bivariate normal. Let's talk about conditional expectation and variance. So the idea is that the behavior of a random variable changes when something correlated to it or something that depends on it when we observe that, right? Once we observe that, we have more information and we might adjust our expectation accordingly. So let's define, we're going to define E of y given x and var of y. So these are the expectation, conditional expectation of y given x, conditional variance of y given x. And we define it by, for specific values, little x, these are, first, it's the expectation of y with respect to the conditional mass function of y given x in the discrete case, or the integral with respect to the conditional density in the continuous case. And the variance we define the same way. The variance is, so the conditional variance okay, so what was the definition of variance? Remember, we defined it as expectation of the square deviation of y from its mean. Well, in this case, it's the expectation of the square deviation of y from its conditional expectation, and it itself is a conditional expectation. And if we expand this, what we see is we get y squared minus 2y expectation of y given x plus expectation of y given x squared given x. So we're left with expectation of y squared given x minus expectation of y given x squared. So it's the similar computing formula, but involving conditional expectations instead of unconditional. Okay, so let's look at an example. So suppose x and y are jointly normal. Expectation 0, variance 1, covariance rho. Then we've shown up above that the conditional distribution of y given x is normal mean rho x variance 1 minus rho squared. And so this tells us that the conditional expectation of y given x equals x is rho x. Conditional variance of y given x equals x is 1 minus rho squared. So actually the conditional variance doesn't change with the value of x. So some observations is that the conditional expectation has all the usual properties of expectation. Because it's essentially defined as the expectation computed from the conditional distribution. So it's expectation on the reduced sample space. So we're saying, okay, sample space started out as omega, but now that we've observed the value of x, it's the subset of omegas such that x is equal to x. This is sometimes written as x inverse of x. And we also have that the conditional expectation of a product of functions, g of x times h of y, given x is equal to x, we can treat the x as a constant, pull it out of the expectation. So it's g of x times the conditional expectation of h of y given x equals x. Expectation of g of x given x is equal to x is just g of little x. And the expectation of y given x equals x is just the value of the expectation of y when x is independent of y. So that's some basic definitions of how of the conditional mean and variance. Next, we're going to talk about conditional mean and variance. So this is thinking of expectation, conditional expectation as an expectation. We can also view it as a random variable, and we'll talk about that in the next video.